talking to us about dynamic van der Waals heterostructures and new electronic phases. So without further ado, I would like to invite him to start with his talk. Thank you.
Afternoon, everyone. It's really great pleasure to be here. So we've been to the old Khalifa, now is the new campus. Really pleasure to see such developments. Thank you so much for the invitation. And again, sorry that we have to leave quite a bunch of us to go for the meeting on the current Khalifa project. So I'll be talking today about the dynamic van der Waals heterostructures, and let me try to explain you, just give you a flavor of what I mean by the dynamic heterostructures. So quite soon after people isolated graphene, many other 2D materials appeared, which is really great because you've got access to the semiconducting, to the superconducting, ferromagnetic materials. In 2D, in physics in 2D would be quite different than physics in 3D, so it's really great by itself that we can study this two-dimensional physics, different types of physics in those materials. But then the next development here is realized when you start creating heterostructures by placing those crystals one on top of each other, and then you can encode many more properties because they start to interact. There is charge transfer in between the layers, so you really can create a number of many more different properties. We're basically talking about a unique situation here where your artificial composite material, this heterostructure, behave as a device at the same time. And the beauty of this technology that if you do everything correctly, the quality which you can gain through this can be really remarkable. So here is one example from some time ago, really, when we created heterostructures by placing two layers of graphene on top of boron nitride, and bilayer boron nitride, and bilayer graphene, bilayer boron nitride, bilayer graphene. So it had a meaning. So like we were trying to make a tunneling device by tunneling through the mid-gap states in the bilayer graphene. But the only reason I'm showing it to you that, for example, if you look at the dark field image, you won't be able to say where your bulk boron nitride stops and where your heterostructure starts. So if you do everything correctly, the quality can be very high. Now, of course, it's not the first time that humanity created heterostructures. So many of us have been working. I mean, I'm coming from 3.5 community long time ago, and so we already had the opportunities of working on those heterostructures before and coding new properties and creating new devices through these hetero interfaces. But there is quite a specific difference in van der Waals heterostructures between van der Waals heterostructures and the usually covalently bonded heterostructures. So usually, of course, it's very difficult to achieve perfect epitaxial stacking. It pretty much never happens. So you always have some strain to be released, but the way how to release strain in the two materials is slightly different. So in the van der Waals heterostructures, what you usually see, there would be some more pattern formation and then atomic reconstruction within this more. In the covalently bonded heterostructures, you don't have this freedom, this flexibility. So typically, there is a lattice mismatch. There are huge strain field being grown, which create defects, which we actually learn how to use. So we create quantum dots based on this technology. But it can be quite a different way of thinking about those interfaces. And now you could imagine that once you have this Moore pattern formed, you have many different stacking within one unit cell, and you have to average against them. Some of them would be more favorable than the others, and then you can plot a diagram of the energy landscape averaged over a unit cell, and then you would have to put quite a lot of different energies, like from van der Waals, of course, elastic. That's at least in the simplest possible case, but then it could be Coulomb, it could be piezo, and so on, and you can plot it as a function of some atomic coordinates or the configurational coordinates. The easiest way, if you start rotating those crystals, you can plot what's the energy of the unit cell as a function of the angle, for example. And we know that there is usually, if you take one interface, usually there would be one global minima, and then a number of the metastable states. And we all learned about this some time ago, because even if you take natural graphite, for example, then the lowest energy state is the so-called Bernal graphite, the ABA stacked. We all know this, but at the same time, not that high, much higher in energy. There is also the so-called rhombohedral ABC graphite. In nature, 85% of our graphite is Bernal stacked, 50% is ABC. And actually, just want to mention that recently there was a revival of interest towards ABC graphite, and you can get it experimentally simply by sliding one layer. So there are different techniques now how to produce it. And the difference is that ABA is a little bit boring, but ABC can be a topological material. So what we also saw that quite interestingly, you can say prepare your material in this metastable high energy state, but then under some conditions you might be able to see it's moving. So you could actually see physically under the microscope those plates microscopically rotating or microscopically moving to adjust into the lower energy state, and that's basically a phase transition. The only problem that ideally you would love to be able to control this phase transition somehow, but if you only got a limited number of parameters, if it's a simple structure, so then it's usually van der Waals against elastic, and it has this one global minima, and once you stuck in it, you just stuck in it. So ideally, you need some extra knobs which you would be able to control, and then you might create a little bit more interesting energy landscape. And usually, it's either pressure or charge, like Coulomb interaction, maybe magnetic field. I'll talk a little bit more about this. And then so your energy landscape starts to become three-dimensional, and by controlling those parameters, you might be able to go back and forth between different phases in the configurational state. So just making this or another one more energetically favorable, and that's great because it leads us to the controllable phase transitions. And these days, phase memory, for example, is becoming very, very important. So that's really allows us to control the phase transitions and create memory devices. Okay, so now, as I said, in the traditional van der Waals heterostructures, it will be a little bit difficult to control because you have elastic and van der Waals, and they basically just give you one solution, one global minima. So what we try to do in our case, we try to introduce a third one, Coulomb interaction as well, so which is usually not that important for in terms of the stacking, and we try to couple it to the van der Waals, but also I'll show you later maybe to the elastic part of the part of the energy. And so here we in our devices, what is important for the rest of the talk, we chose we made two particular changes to how heterostructures are created. One is that we use double aligned heterostructures. So usually, if you had single aligned, you would only get single low energy state. For the double aligned, you already have opportunities for the two competing phases, like in ABA or ABC graphene. And another one, to enhance the strength of those interactions, we use monolayer interfaces. So in this case, we use monolayer graphene, but also monolayer boron nitride, because once you allow monolayer boron nitride, you enhance the strain field dramatically. The reconstruction is much stronger. So here is the Moira pattern from monolayer graphene on monolayer boron nitride, and if you look at the corrugation, which is if you look at the corrugation, you can see that it is larger than 1 nanometer. So typically for the Moira pattern, you would get into the hundreds of less than 100 picometers. So here it's a nanometer. So it's orders of magnitude higher, which enhances many of the phenomena. So now, unfortunately, I'll have to get a little bit technical here just to demonstrate what kind of new phenomena we can see in such heterostructures. And I will be using two type of devices. The physics is pretty much essentially the same. It just one is more one is different type of phenomena at different angles would be easier to be demonstrated in one or another. So in both cases, it's graphene, which is doubly aligned to boron nitride from the bottom and from the top, and it is essential, absolutely essential in our case, that one of the boron nitride is a monolayer. That enhances the effects dramatically. We just in one case we just use bulk BM, graphene monolayer BM, that allows corrugation in the third dimension to be enhanced. But if we want to demonstrate some of the electronic properties, then top gate start to be important, start to be not essential, but important. So it is encapsulated. It kills this corrugation into the third dimension a little bit, but it allows you to see some other effect. So we just start with this simplest one. The structure with single back gate, and you could, because it is exposed to the air, you can do the IFM. You can see all the Moira patterns in the FFT. You see the presence of the two Moira patterns, two hexagons, is because of your graphene is now aligned to both bottom boron nitride and to the top boron nitride. And you can also see it from from Raman as well. If you measure 2D peak, it would be like 70 inverse centimeters, really broad, and it shows you that your strain is strongly accumulated now in graphene. If this is singly aligned, then it would be about 30 maybe. If it is and if it is double, it may be 45. So the presence of monolayer and double alignment really shoots the stars up to 70. And then you do the usual measurement as a function of gauge. You change the carrier concentration in your graphene, and every time you go through the Dirac point, the resistance of course goes up. You don't have the electrons there to conduct, and then there are additional peaks, which is the secondary Dirac point, where your electrons start to scatter on the Bragg scatter on the Mora pattern. You get additional peak in the resistivity, and that basically gives so in our case it corresponds to the two. So we have two peaks because they're slightly misaligned. So one corresponds to one Mora pattern, one corresponds to another Mora pattern. What is though very unusual for in this case is that this device is doped. It means that your Dirac point is not at zero gate voltage. So you need to add holes into the system to reach to the Dirac point. And what is also a bit unusual that this doping, if you recalculate, so this the top axis is the number of electrons per plaquette, per unit Mora pattern. So at the bottom is the number of electrons per square centimeter, just capacitance, or at the top is number of electrons per plaquette, and you see that the doping is such that it's exactly 2 electrons per plaquette. So somehow the system knows that it needs to be in quantized doping state, exactly 2 electrons per plaquette. And then it actually turns out that it's quite strange that if we dope very strongly, so if we dope with p-type a lot, then if we go with n-type a lot, then the system switch. So now from the blue curve we go into the red curve, and the Dirac point now switches to the n doping. But again, it's still integer number of electrons per plaquette. So we had 2 holes per plaquette originally, and it turned to be minus 4 electrons per plaquette doping. Now, I can imagine that there might be criticism that you guys don't know how to make your devices. Singapore is very humid. You get lots of water, whatever crap inside. Believe me, we do know how to make our devices. If there is no monolayer HBN, we only change one thing. We don't have any of this strange effect, no doping, nothing, so no transition, so with very sharp Dirac peaks, so very high quality, high mobility of the devices. So we do know how to produce. It's a real effect which is associated with this double alignment and the presence of the monolayer HBN. Now, a similar situation happens in the encapsulated devices with the top gate. So it's in this case it's not doped before the transition, but that you can still make a transition, and then it goes into n doping, but again it is integer number of electrons per plaquette. So it's a quantized doping. So just maybe to summarize all this transition story for you in one cartoon. So you just measure the resistance curves of this device. So it's very standard. Everyone been measuring it since donkey years. There is a Dirac point. And it is fixed. If you don't charge the system too much, it will be completely reproducible. Nothing happens. But if you go above a threshold, if you do n-type doping above a certain threshold, suddenly there is a phase transition happens, and again it will be a stable phase, and your system is stuck there. But then you go to the negative voltage, and you switch back into the original state, and then you can do this switching back and forth multiple times, so it just works like a clockwork. Just maybe to show that this effect, so it's pretty much always in those devices we see that it's integer doping of integer number of electrons per Planck head, but then of course by varying the angle of the device we can change the size of the Moore pattern, and typically the larger the better alignment, the larger is the Moore pattern. We get higher and higher doping for the so on the left hand side for the single gated, you see that both the initial state grows in doping, and the doping is always larger in the state after transition. But again, it's always integer number of electrons per Planck head. So now let me give you the answer what is going on and how can we use it. And there are basically two effects. One is the phase transition, and it's a structural phase transition. We are lucky that it's coupled to the electronic one as well, but largely what is behind is the structural phase transition. So as I said, if you have doubly aligned system, it's kind of akin to your tri-layer graphene, and you can imagine that it can exist in two different high symmetry configurations, and we actually can see those in our STM imaging. So one is similar to the ABC rhombohedral graphene, just the two outside graphene layers here are replaced by boron nitride, but the symmetry is essentially the same. Or after the transition, we see that one of the layers slide, and then you find yourself in a different symmetry configuration. Your Moore pattern, your reconstruction is now hexagonal, and it corresponds to the ABA Bernal kind of stacking, but again, just you have boron nitride instead of graphene. And if you think if you calculate the energy of those, I won't go into details, but basically you are dominated. So your energy here is pretty much dominated by the energy of the largest reconstructed domain. And it turns out that it depends which one wins, ABC or ABA configuration. It depends a lot on the charge on your graphene, which is not possible to do in the tri-layer graphene, but we can do it in this heterostructure. And it's quite easy to see why is it happening. Like here on the right hand side, right bottom diagram. So the red atoms are the boron atoms, and boron atoms are slightly positively doped due to the covalent bonding to nitrogen, and so we have a little bit of the positive charge sitting on them. But now, imagine if I charge graphene with the negative charge, they interact in the attractive manner. So these configurations start to be more energetically favorable. Now on the left hand side there, again we have our boron being positively charged. But now if we charge graphene positively, so we have holes there. So suddenly there is a repulsive interaction, and which drives this state higher in energy, is becoming energetically unfavorable, and it wants to switch into the other one. So that's basically the nature of our transition. So here we use Coulomb interaction, Coulomb charges on our graphene, which controls the interaction between the two boron nitrides and controls the interaction between graphene and boron nitride. So that's basically in the essence how do we drive these electronic transitions. But usually it would be very, very difficult to see because, well, it changes the local symmetry. Yes, it's the first order phase transition, but unless you've got STM there, it's very, very difficult to observe. So luckily it is coupled to the electronic phase transition as well, which gives us this integer doping, which is by itself a very strange effect. So integer doping, pretty much you don't see it in the two-dimensional systems. Integer doping is like Coulomb blockade in your quantum dots, but to see it in the two-dimensional systems it's pretty much never happens. So what's going on there? Now we have to realize that if we have monolayer boron nitride, as I said, the reconstruction is extremely strong. So your 2D peak is 70, so it means that there is huge amount of strain accumulated in the system. And if we start plotting the strain, you see that it's reconstructed flat on the inside of the domain, but in those vertices, so you have huge strain accumulation, and as you know, certain type of strain leads to the formation of the pseudomagnetic field. So it looks like your sample is now pierced with the magnetic pipes, and the magnetic field inside of those. It's not real magnetic field, right? It is coming from strain that electrons now have to move in a curved space. So it's topological in a sense, but the magnetic field inside of those pipes can be very high, can be like hundreds of Tesla. And that's the beauty of graphene, that whichever magnetic field you put, there is always, you are guaranteed that you have a Landau level sitting at zero energy. So in our case, what it means that you have a flat band sitting exactly at zero energy. So that's this red band. Now is the same after transition. You also have, but here you have twice more of those vertices. So you have two of those flat bands which correspond to the zero Landau level. But of course those vertices where strain is focused, they experience slightly different electrostatic field as well, and it's coming both from the scalar potential, but also from the van der Waals potential, and they are roughly the same in terms of the value. Very difficult to discriminate, which basically pushes this Landau, these flat bands, a little bit up or down. So in this case, it pushes it down, and it hybridizes with the electronic band. So in the right case, it pushes it up, and again they hybridize with the electronic bands, and that exactly gives you doping, finite doping in terms of in the electrically neutral system. So let me just simply give you a bit of a cartoon here how it works. So this hexagonal pattern here is the Moira pattern, and you have a reconstructed domain, and inside of the domain nothing really happens. So it's more or less the same Dirac cones, but when you get to the vertices, instead of the Dirac cones, because of the high magnetic field, pseudomagnetic field, you split the spectrum into the series of Landau levels. And the most interesting for us is the one at zero energy, which is, as usual, would be half field. So it's 4 times degenerate, 2 spins, 2 valleys, and it's only half field, so it has two electrons there. But now the electrostatic potential pushes it up or down, and then if it pushes it up, those electrons, they don't want to sit here. There is energy transfer, so electron transfer into the domain, and basically what you see. So you have a charged quantum dot in the vertex, but it doesn't participate in ion transport, and the rest of the system now is doped, and it's doped exactly with two electrons per quartet. So this is more or less a happy picture, though. Of course, it's not that simple. So it's massively simplified. And I'll just highlight a few interesting stories here, how why it is simplified, and where further interesting physics can be. So I showed you that the origin, so you can think about this as a single Landau level, which pumps electrons into the continuum. But you can take a different approach as well. You can think, okay, how many electrons can I transfer? And there is a very simple formula. There is a global flux for your sample, and you divide this flux by the flux quantum. So that's how many electrons you can get from this. But this flux, it doesn't know about the Moira pattern at all. So it just local strain. So it's the combination of strain and the van der Waals, and it doesn't need to be an integer number at all. So how do you connect these two? So apparently there is a linkage between the local flux and the strain, and basically the reconstruction, the strain reconstruction, is now sensitive to the electron-electron interaction inside of those flat bands. And for me, it's quite a nice story, because now you coupled electron-electron interaction to the strain reconfiguration, which is quite a rare event. There are only a few papers on this. I won't go into detail now, but it's the strange situation when the strain fields are coupled to electron-electron interaction. So it's something to be studied still. And then we also have in most cases we would get integer doping there, but sometimes we get we get even doping there. It's always integer, but we get even doping, which is fine. So how would you uncouple spin? But sometimes we see quite robustly to have odd number of electrons. That's something which we don't understand, but that's probably another level of the electron-electron interaction being reproduced there, because it's something which can lift the spin degeneracy. And so I showed you how to control this behavior before, but strangely enough, now magnetic field can control this phase transition as well. So we can control this phase transition by electrostatic forces. We can control it by temperature. So it's a normal first order phase position, but strangely enough, we can control it by magnetic field. So this is the standard Landau-Hahn diagram, and you can see that we always go above the threshold electric field, but no switching occurs. And then you go to lower magnetic field, and suddenly you switch into the new quantum phase. So which is doped and so on. How magnetic field influences this behavior, we really don't understand. The only clue I can give you here that the magnetic field, when it happens, when this phase transition is triggered, is somehow the magnetic lens becoming of the order of the Moira pattern. So it's roughly 4 Tesla. 4 Tesla is what 12 nanometers, right? So that's becoming, but it's still very puzzling, and it's still something which we don't understand. Now I promised to finish early because we need to reward the best posters and the students with the best posters. So let me skip the end. Just let me put a few conclusions here. So what is most important here is that we need to remember that our van der Waals heterostructures, they're not just carved in stone, unfortunately. So they are fluid systems which we can control and we can arrange phase transitions, and that can give rise to new devices like memory devices, for example, especially smart devices now. Because if you have memory, so you can build probably like memory applications based on that. Then another take-home message is that the flat band. So we usually think about flat band originating from the van der Waals interaction. So here, flat bands are originating from the pseudomagnetic field, and that's surely important for the development of the twistronics, where we want to control electron interaction. And so something which we still don't understand well, but hopefully it will be developed further. That looks like electron interaction can be coupled to the strain degree of freedom, which would be very new and very unique for the van der Waals heterostructure, but also to the magnetic field. So I'd like to thank my collaborators, so quite a few people being involved in this and related kind of work. So there's a series of work now being done. But before I stop, I'd like to also advertise our conference. So last year, this year in July, we had the first edition of AI for X conference. X stands for physics, material science, chemistry, biology, finance, you name it, mathematics, importantly, you name it. And next year it's going to be twice bigger because we're collaborating now with Toronto Accelerate Consortium. So all the robotics people are going to come to Singapore. So I would like to welcome you there as well. So thank you so much for your attention.
Thank you, Kostya, for a wonderful talk on van der Waals physics of 2D materials. I will take a couple of quick questions before we move to the award ceremony. So if anybody in the audience has a very short couple of questions, please raise your hands. Okay, okay, Dr. Dolaver.
Thank you so much. Impressed thoroughly. So our question is about the defects. Could be structural defects, could be impurities. If you guys look into their effect, this is one question. The second question is about the scaling. How much like these effects are available at a certain scale length of the 2D materials. So scaling has some contributions towards this.
Right. So in terms of defects, typically, at least you can't study every single device, but for in TEM, but I mean, our devices are repeatedly. So we get now to the level of 40 million mobility, so much above even gallium arsenide. So in that respect, so defects within the crystals themselves is negligible. So the problem, of course, is always about the interfacial defects in the van der Waals heterostructures, which was a source of huge confusion in the twisted community. But in this case, we know that it's a different effect. So typically, those twisted defects they would be very sensitive to the displacement electric field, which we see from the work of the other groups. Also in other cases as well. These guys, so this effect is not sensitive at all to the displacement field. So we know that it's not coming from one of the interfaces. It's purely Coulomb interaction. Now the second question you mentioned is the scalability. So typically our structures are quite small, so it's basically a few microns wide, whole bars. That was a little bit worrying for us that it's supposed to be first order phase transition, but the first order phase transition should go through the nucleation effect. But luckily we have, to be honest, one device only where we see the domain wall propagation through the sample, so which sort of confirms our assumption that it should be first order. But also I should say that it's much more complex than that, because you don't need, if you have more a pattern, you don't need sliding transition. It can be local change of the rotation, with the global rotation kept constant. So technically how the phase transitions can be arranged, it's in such a complex double Moira patterns can be very complex. So, and I guess there is a selective conditions which can lead, especially on the large scale, to the formation of the domain walls. In the majority of the small devices, in the mesoscopic devices, we don't see this.
Thank you. In the interest of time, may I have please on stage Professor Hassan Arafat, Dr. Antonio Correa, Dr. Mahmoud, to go to the stage for the award ceremony, please.
Thank you very much, Professor Novislov. It's been really a pleasure to have you with us. I would like also to invite Professor Yuri Gumutsi, who is the co-chair of the judging panel.